Have you ever really stopped to think about what's going on deep inside your computer? I mean, really deep. Today, we're going to pull back the curtain on its hidden brain, the kernel. And we're going to explore the two major competing ideas for how that brain should be designed, a choice that affects everything your machine does.
So let's start with something simple. You see an icon on your screen, you click it, and poof, the program opens. Easy, right? Well, not quite. Underneath that simple action, a whole storm of incredibly complex, lightning-fast events gets kicked off. Your request has to travel from your app down through the operating system all the way to the physical hardware. And the one thing conducting that entire orchestra is the kernel.
Now, to really get what the kernel does, you first have to understand that your computer's memory is split into two distinct zones. First, you've got user space. That's where all your normal applications live. Your browser, your games, your music player. They have limited permissions. But then, there's kernel space. Think of this as the VIP section. It's a protected, super privileged area with full control over everything, and nothing from user space gets in without an explicit invitation.
And that's where the kernel lives. It is the absolute core of the operating system. It's the very first program to load when you turn your computer on, and it never, ever leaves. You can think of it as the CEO of your computer. It has total control, it decides who gets to use resources like the CPU and memory, and it's the ultimate translator between your software's requests and what the hardware actually understands.
Okay, so managing everything is a pretty huge job description, right? So let's break it down and focus on two of the kernel's most critical responsibilities. First, juggling all the programs you're running, and second, handling urgent signals from all your hardware.
First up, process management. Right now, your computer is doing dozens, maybe even hundreds of things at once. The kernel's job is to be like an air traffic controller for all these running programs, or processes. It is constantly juggling them, deciding millisecond by millisecond, okay, you get the CPU now, now you. And that juggling act is the magic behind modern computing. This ridiculously fast switching between all the different processes is what creates the illusion that you're listening to music, browsing the web, and downloading a file all at the exact same time. Without the kernel's expert process management, your computer could only do one single thing at a time. All right, the kernel's second huge job, interrupt handling. You can think of an interrupt as a doorbell for the CPU. Every time you press a key or move your mouse or a new piece of data arrives from the internet, the hardware sends a signal that basically screams, "Hey, I need your attention right now." The kernel has to immediately stop whatever it's doing, answer the door, and then get right back to what it was doing before. And this whole process is incredibly precise. The moment that interrupt signal arrives, the CPU just stops. It saves the exact state, we call this the context, of whatever program was running. Then it switches into that privileged kernel mode, runs the special code to handle, say that key you just pressed, and then it restores the original program's context and carries on like nothing ever happened. And this happens thousands, if not millions of times a second.
Okay, so we know what the kernel does, but how do you actually build one to handle all these jobs? Well, that brings us to our tale of two kernels. And first up is the classic, the all-in-one approach, the monolithic kernel.
A monolithic kernel is, well, it's pretty much exactly what it sounds like. It is one single, massive program. Everything. Process management, the device drivers, the file systems, the networking code, it all runs together in that same privileged kernel space, all sharing the same memory. It's one big, happy, and very powerful family. So why do it this way? The main advantage is one word: speed. Raw, blistering speed. Because all the different parts live in the same space, they can talk to each other incredibly fast. If the file system needs to talk to a hard drive driver, it's just a direct function call. There's no complex messaging, no overhead. This makes for a very, very high-performance system.
But, and this is a huge but, there's a massive trade-off. This all-in-one design means there is zero isolation. A bug in a single, seemingly unimportant part, like your printer driver, can bring down the entire operating system. It's a house of cards. And because everything is running with the highest level of privilege, it's also a much bigger target for security attacks.
Now, that inherent instability led a lot of designers to think, there's got to be a better way. And that led them to an entirely different philosophy, a more modular and minimalist approach called the microkernel. A microkernel takes the exact opposite approach. It strips the kernel down to the absolute bare essentials. Basically, just a way for programs to talk to each other and some very basic scheduling.
Everything else, your device drivers, file systems, network services, all of that gets kicked out of the privileged kernel space and runs as its own separate, isolated program in the much safer user space.
And the benefits here are the mirror image of the monolithic kernel's problems. If a device driver crashes, no big deal. It doesn't take the whole system with it. You just restart that one little service. This isolation is a huge win for security and makes the whole system way easier to maintain and update, because you can swap out pieces without ever touching the core kernel.
So what's the catch? There's always a catch, right? Well, it's performance. In that monolithic kernel, all the parts talk directly. In a microkernel, a service has to send a message to the kernel, which then passes the message to another service. All of that message passing adds overhead, which makes a microkernel-based system inherently slower for a lot of tasks.
And this right here sets up one of the longest-running, most passionate debates in all of computer science. It is the classic engineering trade-off. Do you build for raw, unadulterated performance, or do you build for rock-solid stability and security?
So let's just put them right next to each other. You've got the monolithic kernel, like Linux, where everything is integrated into one space for maximum speed, but the trade-off is lower reliability. And on the other side, you have the microkernel, like QNX or Minix, which prioritizes that amazing stability and security by keeping everything separate, but it pays a price in performance because of that message passing overhead.
Now, this whole debate got famously heated back in the day between Linus Torvalds, the creator of the monolithic Linux kernel, and Andrew Tannenbaum, who created the microkernel Minix. You'll sometimes hear about hybrid kernels, things like Windows or Mac OS. But as this famous quote from Linus suggests, a lot of purists will argue that's just marketing. If your device drivers and file systems are still in kernel space, it's fundamentally monolithic.
And that brings us full circle, right back to where we started. That simple click you made, it kicks off a whole chain of events: process management, interrupts, I/O requests. And the speed, the stability, and the security of that entire process are all dictated by this one fundamental architectural choice that was made by the operating systems designers years and years ago.
So here's the thought I want to leave you with. As our devices, from our phones to our cars to critical medical equipment, get more and more complex and more connected, the stakes in this debate just keep getting higher. So which will win out in the long run? Will it be the blistering speed of the monolithic design, or will the undeniable security and reliability of the microkernel ultimately prove to be more important? The tale of these two kernels, believe me, is far from over.